Hi, this is a recorded lecture for the IB DP Design Technology. We're looking at structural systems, force diagrams in particular, and this is topic B3.2. This is HL content, design in practice. So from the IB, you need to understand how static and dynamic forces act. You need to be able to know how this can be represented diagrammatically. So one of the ways that we represent forces diagrammatically is using a force diagram or a free body diagram. And these are diagrams that are used to show the relative magnitude and directions of all forces acting upon an object in a given situation. And you normally see them sort of like in science looking like this, where you're showing an arrow with the direction that a force is acting, and the size of the arrow determines the magnitude or the amount of force acting. So typically when we look at these force diagrams, we use certain forces. So for instance, there's an applied force. An applied force is usually represented with a capital F with a subscript APP. So this is applied force. And this is a force that is being applied to an object by a person or say another object. If the person is pushing a desk across the room, there is an applied force acting upon the object. The applied force is the force exerted on the desk by the person. So you can see this is an image of a person pushing a box. Now, something important is once this person stops pushing, the force is no longer applied. And so this is really important. So like for instance, if this person stopped pushing and this box was to continue to slide along, there is no applied force. The applied force is when the person is pushing. When they stop pushing, there is no longer an applied force. Gravity is represented with an F and a subscript grave. And if you look here, it is the force of gravity, which acts on the Earth, Moon, or other massive large objects, and they attract others towards themselves. By definition, this is weight. All objects on Earth experience a force of gravity. It is directed downwards towards the center of the Earth. The force of gravity on Earth is always equal to the weight of the object. So weight and gravity are essentially the same thing. And you need to always understand that this is a downward force. So typically in our force diagrams, gravity is going to be downwards. The normal force is a force that is a supporting force and it's exerted on an object that is in contact with another stable object. So for example, a book is resting on a surface, then the normal force is being exerted upwards in order to support the weight of the book on the table. Sometimes the normal force is exerted horizontally between two objects that are in contact with each other. For instance, if a person leans on a wall, then the wall pushes horizontally on the person. But typically the normal force is perpendicular to whatever surface is in contact with the object. So this is actually interesting. If you have an object that's on a ramp, the normal force will be perpendicular to the angle of that ramp. So it's always perpendicular to the surface. And so in this example, if a person's leaning against a wall, the normal force will not be vertical, it'll be horizontal based on the person leaning on the wall. Friction is, of course, a force that acts between surfaces of objects when they move past each other, and we represent that with a subscript fric. Friction is caused by intermolecular attractive forces between molecules of different surfaces. Air resistance is a special type of frictional force. This acts as an object is traveling through the air. The force of air resistance is often observed opposed to the object motion. We don't really need to worry about air resistance in a lot of our designs unless you're talking about something that's going to be interacting with the wind, in which case you are going to be dealing with air resistance. So like an umbrella or a wind turbine, these things interact with the wind, and therefore you're going to have to take into account things like the force of air resistance on those particular objects. Tensional force, this is one that we definitely want to think about within design context. So this is the force that is applied and transmitted through a string, rope, or cable. We represent it as tens. A spring force is the force applied by a spring. Again, we don't necessarily need to learn this as much as just understand that this is a force that we might deal with. So I want you to think about what forces are acting here on this flying squirrel. If you said that there was air resistance and gravity, then you're correct. What forces are acting here? We have a weight acting downwards, so that's a gravitational force, and then a normal force acting up. Presumably this athlete is holding this weight steady or stable or static, and therefore there's no applied force. It's only the gravitational force and the normal force that's acting here. If we think about this, we've got friction with the cork in the wine bottle, and then we're going to have a torsion as you spin this bottle opener. Here we're going to be dealing with gravity and tension. Here we're going to be just dealing with compression and gravity. We need to think about how these forces work in structures. And so one of the main ways that we see this is with compression. So if you think about this, you've got a mass and it's being pulled down by gravity. So you've got weight, and of course it's going to compress, for instance, right here, this is like a lintel between, or a beam between two uprights, between two columns, let's say. And so you're going to have this force of gravity pulling down on this, and you're going to have compressional forces on the top and tensional forces on the bottom, because this is going to want to split here because it's being pulled apart, whereas up here we're squishing things together. Now, we also have to think about things like arches. So when we look at force diagrams in things like arches, you might understand that the force of gravity is pushing down, but it gets sort of deflected down into the uprights of the arch by these stones up here. And they also have the tendency to be pushed apart. So this is a problem that people have been dealing with for hundreds and thousands of years. And so one of the things that they would do is they would use buttresses. So they would have a structure on the side of the arch to make sure that it counteracts this force of tension, which is pulling this arch apart. Same thing with a pointed arch. You might also use something called a flying buttress. In this case, this is same idea, but you want to redirect that force, that tensional force that's pulling the arch apart, downwards into a compressional force. This is an example of that. So if you think of Notre Dame Cathedral, this is a flying buttress, and this is holding up this dome right here. And you can see all of the forces involved here. You've got normal forces and compressional forces and tensional forces all acting in this building, and the flying buttresses are helping to keep this building upright. We also need to think of tension. And so, for instance, if I'm holding up the mast of a ship, I'm going to be using something called stays. And that's what these are right here. These are stays, and they're a cable which is under tension. And essentially you have 4 stays holding up this mast. You've got one on the left, one on the right, these stays right here, and they are tensioned to hold this rigid. Then you have to do the same thing with the forward and backward. You need stays there. So you're gonna have a stay that's on the back and on the front. And those are gonna hold this mast in place. You can see the same thing on this. This is a antenna, and you can see this guy wires. These are called guy wires here. And there are also 4 of them acting in opposite directions in order to hold this antenna up. Now, you don't always have pairs of guy wires. This is another example of guy wires. So this is a telephone pole, and you have the guy wires over here on the right-hand side. And these are acting in opposition to forces that are pulling this telephone pole to the left. So the wires that are coming out of the telephone pole here, they need to be counteracted using these guy wires. Otherwise, this pole would tip over towards the left. And so that's what these are all about. They're counteracting these wires right here that are going off to the left. When we think about this, what we want to do is maintain equilibrium. So essentially, we want the same amount of tensional force acting in opposite directions. And that's what's happening here with one of these famous Tenzin sculptures. The tension of these 2 counteract the tension of this. And then you get equilibrium, or a balanced force. And there will be, when forces are balanced, you don't get any movement. This is another example of equilibrium. You can think of this with lintels. And so you'll have your compressional forces and your tensional forces, but they're counteracted, and so nothing is moving. And Stonehenge is a famous example of that. And then also something like the Parthenon in Greece. Here's some other examples of equilibrium: a sign with a angle right here that makes a triangle. So that's going to hold this and make sure that it is in tension, and also it won't be moving. So it's at equilibrium. Same with an arch, and arches can last a very long time. I'd like you to practice some of these free body diagrams. So this is an interactive that you can use to practice free body diagrams. Thank you for watching.